Another algorithm that we can use for these shortest path problems is the Floyd Warshall algorithm. It actually solves the all pairs shortest path problem, meaning that it would provide us with the shortest path between any two vertices in our graph. But of course, we can use that for the single start location problem that we've been looking at. It finds the paths between all of the pairs of points in the graph and, in fact, finds the minimum path between all of them. It can handle negative weights, like the examples that we've seen before, but it cannot handle negative cycles where you could infinitely decrease your cost. For example, getting from C to D to B, back to C to D to B. If, for instance, you were asked, what's the distance from C to A? Then the best to do with negative cycles is to loop through this negative cycle infinitely and decrease your cost infinitely before jumping from C to A. And so that will pose a problem to it. But if it only had a negative edge and no cycle that you could loop through and infinitely decrease your weight, then the Floyd Warshall algorithm will handle that. The main idea is keeping a matrix of all pairs of vertex to vertex. And then we work through each vertex, deciding if the path between a pair A and B is better with that new vertex V that we're looking at or not, by looking at the cost of the path from A to V and the cost of the path from V to B. So we may have a direct connection from A to B, for example, but it might be better to go from A to C to B. So we would evaluate that kind of question as we process through the Floyd Warshall algorithm. So we've got these two possibilities. We know perhaps a path from A to B, or we assume it's infinite before we've seen a path. And then we see a new vertex V, and we ask, well, would it be better to go from A to V and then from V to B? And it may or may not be the case. Maybe going through V, it may be true that going through V doesn't help and doesn't shorten our path, and it may be true that going through V does provide us with a shorter path. So we start with two vertex by vertex matrices, or cardinality of vertices by cardinality of vertices matrices. That's hard to say. Indexed by the vertex, so that we could do things like look up the row for A and the column for B. It tracks the distance, meaning the minimum path lengths, which are all set to infinity to start with, and it tracks the next vertex in a path, which of course all start out as null. We add each edge that connects vertices U and V, we'll call them here, and we store its weight in the distance of UV, and we store V in the next of UV. So we're able to update a distance for that particular connection as we see an edge between them, and we're able to store that V is the next to go to from U, for example. Then for each vertex, we loop through all combinations of A, B. So we're going to look at all pairs of vertices, an expensive operation, certainly. And if the distance from A to V plus V to B is less than the distance of A to B, then we'll update the distance of A to B with that smaller value, and we'll not update the next of AB with the next of AV, meaning that we will connect this AB path to the A to V path. We'll make it so that if I'm starting from A and I'm wanting to get to B, I will notice whatever the next step is on that path from A to V uses V as kind of an intermediary there. Here's a small example. So we've got a graph here. We start off with the costs of the direct connections between them. A to C has a cost of 7. A to B has a cost of 4. B to A has a cost of 1. So this is a directed graph, you'll notice, and the weights are different in different directions. And the next will only be what they can directly connect to. So if you're trying to get from B to A, well, the next is A because they have a direct connection. And if you're trying to get from C to A, then the next is A because they have a direct connection, and so on. So then we're going to go through each vertex and we're going to ask, what if we updated paths through there with the costs associated with those vertices? So for example, you see there's not a direct connection from C going to B, and so it had infinity as its cost. Well, if I look through here and I look at A, I can use A as an intermediary to get from C to A and then A to B. So that means that my cost there can be updated to 10. The other costs won't change because they're all direct connections with A. Then for B, we can update the cost to get from A to C because we can actually get a cheaper path going from B to A and then A to C. And so that provided us with a better option that we can update our table with there. And it will tell us that from A, the shorter path is to go from A to B and then B to C. And so the option is that if I'm going from A trying to get to C, the next I would go to is B, and then I look up from B to C, and I know the next I would go to is to get to C from there. And then finally, we'll have to look at C and see if it can be used as an intermediary for anyone. And it looks like it can't because its edges are just too expensive coming out of it that we won't update any paths that way. You can look up more details of the Floyd Warshall algorithm on Wikipedia. It's definitely a useful algorithm for building these large sets of paths to each other. The trick is that it's going to have a triple nested for loop, which is just bad news to hear in general in a computing context. That means that the algorithm has a complexity of the cardinality of vertices cubed, because we're going to have to add the edges into the table. Then we're going to have to take from each vertex to every other vertex to try to do those updates of, can I make a better connection between these pairs of vertices that I see in the table entries here. So it is a hefty algorithm, to be certain. It's slightly better than doing repeated Dijkstra calls for every vertex if it's a dense graph. So if we do need these all pairs answer, it actually is a little better than doing Dijkstra on a graph that has a large number of edges, because Dijkstra's performance relates more to the size of the edges, where Floyd Warshall will deal more with the size of the number of vertices. So it's better than calling Dijkstra over and over for every vertex to say, give me all the paths from A, now give me all the paths from B, now give me all the paths from C. So there's some performance increase for the all pairs circumstance. It's definitely not going to do better than the single source problem that Dijkstra is solving there. But it can handle some things that Dijkstra can't, the negative values. It's worse than repeated calls to Dijkstra on a sparse graph. If Dijkstra was going to do well because the graph was not heavy on edges, then we might as well just call Dijkstra over and over again for those. So we have these two algorithms for finding shortest paths. Dijkstra's algorithm is good for finding from a single source the short paths to other vertices in the graph, and it does its best on sparse graphs that are not heavy on the number of edges they have. The Floyd Warshall algorithm will handle negative weights, which Dijkstra's can't, and it can do well on dense graphs where we really do need to know the distances from multiple sources. And so both of these algorithms can help us to solve problems that we need to know, paths to something. We also can use them for plans, constructing the plan of how we're going to put together a particular machine or how we're going to manipulate parts of a robot into the right configuration or manipulate physical objects or things like that. These problems do generalize very well, and so they're definitely a field worth exploring and understanding some of the algorithms to handle those types of problems. Dijkstra has had some similarities to prims, and Floyd Warshall uses matrix representations, so it's going to use also some memory for that too.